Today we are going to discuss calculation of process and performance parameters of combing machine. We will start with draft. You are all familiar with the definition of draft and what draft basically means in the context of spinning. So, draft in this case, in the case of comber, we can say that the actual draft has two components. One is the mechanical draft and the other one is the draft due to noil extraction. So, the noil or the waste that we extract, we can also say in a way it is synonymous to drafting, because this is going to reduce the linear density of the output from the combing head. Therefore, it is also similar to, in a way similar to drafting, where in the drafting we stress the material, make it finer. In the case of noil extraction, by extracting the noil, removing some short fibers, we are ultimately making the output material finer. So, that way we can also say this is a type of draft. Now, mechanical draft, as you all know, is the ratio of surface speeds of the output and the input rollers, and the draft due to noil extraction is always the mechanical draft that we get into 100 minus 100 minus W, where W is the noil percentage that we get. The major mechanical drafts that we see, they can be again classified into two: major drafts and the tension drafts. The major draft is basically the draft between feed roller and the detaching roller, and the draft that we keep in the draw box, that is where the slivers are actually stretched and combined together on the draw box of the combing machine. So, that is the draft in the draw box, which is very similar to the kind of system that we have on a draw frame. And the draft between the feed roller and the detaching roller, that is in the combing zone, that is also a kind of draft which we call is the mechanical draft, because we can know what the speed of the feed roller, we can also find out the speed of the detaching roller, and taking the ratio we can find out how much is the draft there. The tension draft is, as we all know, is very nominal, and this exists in between first lap roller and the feed roller, then detaching roller and the sliver table calendar rollers, sliver table calendar roller and back pair of draw box roller, then front pair of draw box roller and draw box calendar roller, and draw box calendar roller to coiler calendar roller. So, there are so many places where the tension draft actually exists, as shown here, and these tension drafts are basically very minor amount of draft, hardly the values will be 1.01, 1.02, they are all close to 1. The purpose is to slightly keep the material under little stretch. You are not really going to create sliding action between the fibers. Tension draft purpose is not to really make the fiber slide, but to keep the material under little tension state. That is the purpose of the tension draft. Now, we go to the next slide. The draft, mechanical draft is the ratio of surface speed, as we have stated earlier. So, surface speed of the coiler calendar roller and the surface speed of lap feed roller, if we know, we can find out what is the total mechanical draft in the machine, because we are feeding the lap in one side and the extreme end, the other extreme end is the coiler calendar roller. So, if we know the surface speed of these two, then we can calculate what is the total mechanical draft in the machine. And the actual draft is based on the calculation, based on what? Based on the linear density or hank of feed material, which is lap, and linear density or hank of the output material, that is sliver. So, we can say this is actual draft will be combined linear density of lap feeds whatever I would generally feed 6 laps or 8 laps. So, combined linear density of all the laps, that in kilotex, and then we divide it by the linear density of the saliva that we produce. So, this ratio of linear density is going to be the actual draft. Now, we will make we will give an example of draft calculation, which is based on the density, linear density of the materials of the input and output and the noil that we are going to extract. Now, lab linear density, let us say, is 60 kilotex, atypical. Noil extraction, let us say 20%. Linear density of the saliva delivered is 5 kilotex. Therefore, linear density of the combed fringe after combing, the fleece that we produce, that is called combed fringe in this case. So, that is going to be how much? 60 into 100 minus 20 by 100, what 20% waste we are removing from 60 kilotex. Therefore, basically it is 60 into 0.8, and therefore, it is going to be 48 kilotex, that is the fleece that we produce from each combing head. So, draft due to noil extraction in this case, therefore, we can write is 60 by 48, which is going to be 1.25. So, 1.25 becomes the draft due to noil extraction in this case. Now, as we know, the total draft, total actual draft is going to be based on the linear density of the input and output ratio. Therefore, it is the combined linear density of all the laps fed and linear density of the saliva delivered. So, if we are feeding 6 laps in this case, that is we are having 6 head combing machine, then linear density of all the laps fed is going to be 6 into 60, and the output is one single saliva of 5 kilotex. So, we take the ratio, that gives me 72. So, 72 becomes my actually total draft, total actual draft. Okay. So, out of the 72 total actual draft that we get, the draft due to noil extraction was 1.25, which will be constant for all the heads, because all the heads we have set in such a way that we extract 20% from each and every head. So, the mechanical draft in the machine, therefore, we can estimate from this value without going through the calculation of the rotational speed of the gears. Therefore, we can write that the mechanical draft must be 72 by 1.25, that is going to be 57.5. So, total draft is based on the linear density of the input and output. The draft in the combing zone due to noil extraction is 1.25, and hence the ratio of these two is going to give me the mechanical draft in the machine. This is an estimated value. We can also verify this by measuring or by finding out the surface speed of the input roller, that is lap feed roller, and a surface speed of the output roller, that is the coil air cylinder roller. If we also can do it, that is a very lengthy calculation, because so many gears will be involved there, but one can do it tracing the motion transmission path from motor to the lap feed roller and from motor to the coil air cylinder roller, and if we do this, we will also be able to find it out to check it. Now, how to find out the noil percentage? Noil percentage, we can find it out by taking this ratio. Noil percentage is weight of noil. Noil means the waste or the short fiber that we extract. The technical term is noil. So, weight of Noel and weight of Noel plus weight of saliva produced. This ratio multiplied by 100 is going to give me the Noel percentage in the machine. So, if we want to find out Noel percentage of the machine on a running machine, we can run the machine for a specific time, maybe 15 minutes, maybe 20 minutes, and then calculate, or can we actually collect, not calculate, actually collect the Noel from the machine and also the saliva that we are producing during that particular duration of time. So, if these two quantities are known to me, we can easily find out how much Noel actually the machine is extracting. Next, we go to another important calculation, that is production calculation, because we will be always interested finally in the production of the machine, and the whole commercial activity depends upon the production rate of the machine. So, production in the case of Comber depends upon, you see, so many parameters of the machines. What are those parameters? One is the speed of the machine, then the running efficiency of the machine, linear density of the lap that we are feeding, number of combing heads that you have of the machine. Generally, machines are available with 6 combing heads or 8 combing heads. Most of the modern machines today will be having 8 combing heads. Then how much lap I am feeding per cycle, or per cycle means for every full rotation of the cylinder comb, how much lap is fed. Also sometimes we write it lap fed per nip, that is meaning basically same, and Noel extraction percentage. So, we need to know all this, and all of them will have an effect on the production of the machine. So, if you do the production calculation and the formulas we have written it here, they are very simple. First of all, production per combing head in kg per hour, we have to specify the unit of weight is kg, and we have to find out production for a given duration of time. So, that time let us say is hour. So, 1 hour how much kg we are going to produce. So, it is going to be this in 1 kg how much lap I am going to feed, weight of lap fed in kg, this into 1 minus fraction of Noel that is going to extract, because that is going to be removed from the material that is being fed from the lab. So, that we have to find out how much is this, and that is going out of the system, and hence we have to factor that into this formula, that multiplied by efficiency of the machine. That the machine may stop due to variety of reason and may not be producing the material in 1 hour or whatever time we fix in a shift, it could be 8 hours. If we want to calculate for a day, it could be 24 hours. There will be certain times when the machine will be not in operation because of varieties of reasons. Maybe that could be lap leaking, that could be choking of the sliver, that could be some kind of maybe lapping on the cylinder comb. There are varieties of reasons for which the machine may stop, and therefore, during those period of time the machine is idle, we are not producing anything, and therefore, these parts are therefore affect my efficiency. So, you have to take care of that, what is the efficiency percentage of the machine, and that will give me the production. So, weight of lap fed is going to be how much, length of lap fed per hour in meter into lap hang in kilotex, and we have to know how much lap I am going to feed per hour. So, if I know length of lap fed per nip in terms of millimeter, So, that divided by 1000 will give me the length of lap fed in terms of meter, and then that should be multiplied by nips per minute or the speed of the machine into 60 is going to be the in hour, and then finally, we multiply this by the linear density of the lap or lap hang in kilotex. So, lap hang in kilotex basically means the weight in gram per meter, that is whatever is the lap hang. If I say lap hang is 60 kilotex, basically means that 1 meter of lap will weigh 60 gram. Now, if I do this, we will get this formula kind of simplified 0.06 as shown here in the next line, and weight of lap fed per hour in kg. If I want to know, I have to further divide this by another 1000, because in the previous one line the weight that I am getting, that is in gram. Now, gram I have to convert them into kg, therefore, we have to divide the entire thing again by another 1000. This 1000 is basically to convert gram into kg. So, that is how the previous one is up to 1 hour, that is the weight of lap. So, we could calculate this part only, and this part is what is shown in the last line. The other two parts then we have to know also. So, if I want to find out for 8 hour, I have to multiply it by another, a figure 8 must come here. So, if I want to know per head per 8 hours, then whatever was the previous value, that needs to be multiplied by 1/8. I think the 8 is missing here, we will multiplied by 8. This will give me the production per 8 hour. Now, production for the whole machine, total production, then I have 8 head machines. So, I have to multiply it by another 8. So, the first 8 is because of 8 hours, and the second 8 is because the machine has 8 heads. So, if we do this, then we get this value as written here 0.06 by 1000, 8 into 8, lap fed in terms of millimeter, nis per minute, that is the speed of the machine, then lap hang in kilotex, and now will come the Néel percentage that we are producing, that figure we have to put here, and the efficiency figure also we have to put. That will give me the actual production that we expect. If we know all these values, we will be able to find out what is the total production that we would expect. And if I do this, this gives me this figure 0.00384, then this factor, this you see, that means the total production of the machine in 8 hours depends upon one constant, that is this, then one parameter, one is this one, lap fed per nip in millimeter. Number 2 parameter is what is the speed of the machine, nips per minute. The third is the what is the hang of the lap or linear density of the lap. Then fourth is how much Néel I am extracting, and the fifth is the efficiency. So many 1, 2, 3, 4, 5, they all are going to affect the production per head, production not per head, the total production of the machine is going to be dependent on so many parameters. So, this is how we can calculate, and we can also find out what is the total production in theoretically, and if I want to calculate efficiency, and if I know the left hand side of this equation, efficiency is unknown to me, and I can find out what is the efficiency figure. Now, here we are taking an example. Let us say lap feed per cycle is 6.7 millimeter. Per cycle basically means per nip, meaning the same thing. Noel extraction is 16%, number of heads are 6, linear density is 68 kilotex, nips per minute or the speed of the machine is 250 and efficiency let us say 90%. If this is the data given to you, then you can easily find out how much is going to be the production. First, length of lap fed to the combing heads per hour, we calculate 250 into 60, 90 by 100 into 6 heads are there, 6.7 into 10 to the power 3. This value is basically converting millimeter to meter. So, we find out this is the total length of lap that is going to feed. This is 542.7 meter per minute of lap is being fed. Weight of lap fed per hour, therefore, we convert it into kg. So, we multiplied by the lap hang which is 68 and then divide by 1000 to convert the weight in gram to kg. So, we get a figure 36.90 kg. So, weight of comb sliver delivered will be how much? So much lap is fed. So, lap fed is 36.9 kg. Sliver delivered will be less than this because we are extracting waste. So, therefore, if 16% waste is removed, then the actual production of comb sliver is going to be 36.9 into 0.84. 100 minus 16 by 100 is basically 0.84, and that will give me a figure 31 kg per hour. That means, this machine will be producing 31 kg per hour. From there, another important process parameters we sometimes need to calculate or efficiency parameter of the machine is nap removal efficiency. The comber is also capable to remove the naps which are still left in the sliver. See, after the carding process, still some naps will be left in the sliver, and combing is the last machine in the process where there is a possibility to remove certain amount of naps. So, if we want to find out nap removal efficiency, that is how much naps per gram in comber lap, feed lap, the naps per gram in comb sliver divided by naps per gram in comber lap. If I, that means the numerator will give how much naps have been removed, and the denominator gives how much nap was there in the comber lap originally. So, ratio of these two multiplied by 100 will give you nap removal efficiency. So, typically the efficiency has been found to be varying between 45 to 80% depending upon the level of noil that I am extracting. That means, if I remove 12% or 16%, 18%, 20% noil, the nap removal efficiency will also change. It is a function of how much noil I am extracting. So, the figure therefore may vary depending upon the noil, depending upon the type of machine that is processing the fibers or the laps. So, typical values varies between 45 to 80%. The other thing in which we will be interested is the short fiber removal efficiency of the machine. The machine has been primarily designed to remove short fibers. That is the purpose of the combing machine, main purpose is. Therefore, we must try to assess the performance by knowing also what is the short fiber removal efficiency, and that we can write is that is short fiber present in comber lap, short fiber present in sliver divided by short fiber percentage in the again in the comber lap into 100. That will give me the short fiber removal efficiency, and that value varies between 50 to 70% again depending upon the noil percentage. So, we should remember that somewhere between 50 to 70% is the efficiency of the machines, and one can find out the short fiber removal efficiency using this simple formula. Other thing is, now this another concept is how much short fiber is effectively removed. The point is that while the combing process is going on, some of the long fibers also might break during the combing actions. So, it is not that we are removing the short fibers which are present in the comb lap, but we are also generating, the machine may also generate some amount of short fiber because it is breaking some long fibers, since because of the combing force. So, by doing so, now if some fibers, long fibers are converted into short fibers because of the breakage, then the question comes that whatever short fibers the machine might generate, what is the fate of those short fibers? Are they becoming a part of comb fiber, or are they getting removed by the machine in the form of noil? Both possibilities are there. It is very difficult to know that once a long fiber is broken into two pieces, the shorter part which may fall into long short fiber category, it may so break that one part becomes a may fall into long fiber category, the other part may fall into short fiber category. In that case, the short fiber part, whatever is there, what is going to be the fate, whether it is going to be extracted as noil or whether it is going to be part of comb fiber, we very difficult to say accurately, but this is all is going to happen also. So, let us say loss of, therefore, if you look at the diagram, the noil that we see is because of short fiber removal by the machine, and we also have seen some long fiber loss. We have also studied or also discussed them, that in the noil also we find some long fibers, if you recall, because some long fibers may remain folded in the lap, their extent is becomes too short, and therefore, they behave like short fibers while they are going through the combing zone, and they might be extracted as short fibers, though actually they are long, but because the effective length gets shortened because they are in a folded state in the lap, therefore, they are extracted as short fibers. So, noil may consist of therefore long fiber loss also, and also third part is short fiber generated due to long fiber breakage. That is what I told just now. This could be also contributing towards the noil. So, noil therefore consists of short fibers present in lap, short fibers generated during combing process, and long fibers in the lap itself. So, let N1 is the noil percentage, N is short fiber weight percentage below the boundary length in the lap, and Ws is the short fiber weight percentage below the boundary length in the combed fiber. What is the boundary length? E plus minus f by 2. This was what was also discussed some previous lecture, previous session, is what is boundary length, and we know that any fiber which is less than the boundary length is likely to be extracted as short fiber. Therefore, if these are the values, then the weight of short fiber incorporated in this fiber corresponding to 100 gram of lap is going to be W dash S, which is W S into 100 minus N 1 by 100. What is W S? We have already told in the previous slide, short fiber weight percentage below the boundary length in the comb fiber. So, this is the this area indicates basically Ws, and what is N definition? Short fiber weight percentage below the boundary length in the lab. Therefore, in this diagram, this part is your N. So, this is the short fiber which was originally present in the lab, and now this is short fiber still left in the comb sliver. We have also discussed that why comb sliver also may contain some short fibers. That was also pointed out earlier. This is because some of the short fibers may pass through the needles, of the top comb, because they are attached to the longer ones. There is some friction association between the long and short fibers. So, the long fibers is being pulled by the detaching roller, one short fiber which is attached to it may also be incorporated in the comb sliver, and it may not be sometimes arrested by the needles of the top comb, though purpose of the top comb is to arrest this incorporation of short fibers into the comb sliver, but sometimes they fail because the gap between the needles of the top comb is much larger than the size of the short fibers in terms of diameter size of the short fiber, not the length. Hence, weight of short fibers incorporated in the sliver corresponding to 100 gram of lab is what is given by this formula, Ws into 100 minus N1 by 100. So, the effectively removed short fiber is going to be N minus Ws, W dash S, it is not N minus Ws. Otherwise, generally people will feel N is the short fiber present in the lab, this much is still left Ws. So, N minus Ws is what we have removed, but actually the exact formula is going to be not N minus Ws, but N minus W dash S, and therefore, it is going to be S is going to be N minus W dash S, where W dash S I have shown here, this figure is coming here, and that gives you the effectively removed short fibers by the combing machine. With this, we close this lecture. So, we have discussed few things. What are those? One is what is draft, what is mechanical draft, what is actual draft, what is draft due to Noyal extraction. Then we have found out what is how to calculate production. So, those things have been done. Then we have given the formula of your short fiber removal percentage, we have given the formula for neb removal efficiency. So, these formulas have been given, they are very simple, and we can find out also pretty easy to calculate as well. So, with this, let us close this particular session. Thank you.